very small in comparison to the energy that comes out. So, if there's two things that I'm going to teach you, one thing is about entropy and, intoxication. The other thing I'm going to teach you about is exothermic reactions, right? And reactions that proceed very, very violently. Now, this is a really good example because this is fun. I love this. Because you can feel the impact, you can feel everything, and, of course, it's created. Now, you remember all that when you calculate the formation, you calculate that, you find that the delta H is negative, which means that it's an exothermic reaction. And so we learned right away one of the most very important things about this class, and that is that there's a definite difference between something like hydrogen gas and something like helium gas. That's why nowadays Goodyear puts helium gas in their blimps. Now, if we were to do it look a little bit different and replace the helium gas with hydrogen gas, I mean, come on, it's you or the screen, right? The next class needs to see where they're examining. Normally, I'd like these to be a little bit higher, so this is what happens with hydrogen gas. Right? Now, what you're seeing there, if you remember from the very first lecture, when we were talking about this, what you're seeing in this example is you have hydrogen. This reaction is what's going to occur. Hydrogen with oxygen to form water. Okay? So why it goes boom, boom, boom like that, right? Because the flame goes in, it causes a leak in the balloon, the hydrogen expands out from after the balloon breaks and mixes with oxygen, and then the reaction proceeds and uses the energy of the flame to combust and to form liquid water. Okay? So it's going like, the reason it does that is because you're seeing the hydrogen mix with the oxygen gas. Now, what we can do is we can, it's a little close again, but we'll tell. Mix in the proper mole ratio. Now, I didn't make it. If we mix in the proper mole ratio oxygen to hydrogen and now try the experiment, let's see what's different. Right? And I'm sure you're going to see it's a lot different.
Oh, Jesus.
Right?
So that was awful.
A basic chemistry. 2-to-1 ratio.
I'm so glad I'm not in the front,
right?
like in the
2
beginning.
parts hydrogen,
I felt it hit my
1
chest.
part oxygen,
Oh, yeah.
proper balance
That was insane.
gives you these products.
Wait, that's because level
Exothermic
H2O2.
reaction. Remember what an exothermic reaction
That's not the right ratio. Yeah, I know.
Let's talk about this reaction here. I'm going to do this, and this one takes a little while to get going, and it's unfortunate. But once I get it going throughout the class, I think we can. I don't want to too many things going on.
I'll make it.
Okay, great. The BZ reaction is kind of like a this reaction is, and I have to read about this reaction, so just give me a second. Okay, this is a cycle. This is a time-dependent redox reaction. So we have oxidation and reduction, and it's a catalytic cycle. So it's a lot like, in biology where you learn about the citric acid cycle. So there's a cycle of events, and this is the chemicals involved is, I believe we're using cerium oxide, potassium bromate, sulfuric acid, and iron sulfate. So what happens is you start with one set of oxidation states of the reactant. Then what happens is the chemistry occurs and it makes another state. Then chemistry occurs and it makes another state. Chemistry occurs and it makes another state. And then finally, at the end, you regenerate the initial state. And this continues to go on. Just like any biological cycle, you eventually end up at the very beginning. And this is an example of that. And you can see the cycling by the color change. All right. The rest of the chemistry is more stuff in Chem 2C, so I'm going to steer clear from that. So let me just make sure. It says, are you serious? 500 milliliters, large lecture volume, it says. Okay, chemicals, 1, potassium bromate. Okay, solution A, potassium bromate. Let me dump this in, get it going. Yeah, I find it awfully odd that some of these reactions, okay, I see, 500 mils, can I measure 500 mils? Okay, then it says malonic acid and sulfuric acid, add 500 mils of that. That would be this one. Then 0.2 molar of solution says 10 mils of solution. C. I bet there's some reason they gave me these gloves. And solution C, 10 mils of that. Spinning, take the top part's getting this thing spinning now. And get a good vortex going. That's it. Get too aggressive.
Oh, yes.
Okay, 10 mils of solution C. A little overkill on solution C for 10 mils. Honest, that's solution C. It's not vitamin B complex. And then, lo and behold, solution D, which is the final element of the catalytic regeneration process, 30 mils.
Yum.
Seems every time I do this, it's different. Let's see what happens. Wait for it, let's just watch it. See? Okay, we got some greenish blue. You still have a gradient going through here, which is the way it mixes. And it's a pretty sudden color change. As I recall, it goes green to red. Maybe. Okay, so sometimes things don't work. I don't know why it's not working, but let's just keep watching it. Maybe it just takes a few minutes to get everything mixed from the top to the bottom. Otherwise, no clue why this is not working. So let's move on to the next one, which is luminol. Just keep watching that. Sometimes it takes a few minutes to get going, and then it'll start cycling. Otherwise, I just totally blew it. And I don't know why. So let's move to this one. Can I get the lights when I tell you?
Yeah, can you tell me?
I will tell you. Okay, this, if you remember, is chemiluminescence. We have two solutions here. These two solutions are going to be mixed together, and when I mix them together, chemical reaction is going to occur. Instead of like the normal type of chemical reaction, where you normally think about two molecules coming together in their ground state to form another molecule or a set of molecules as products that are in their ground state, this reaction, one of the products comes out in its excited state. And so since it's in that molecular excited state, it turns out what happens is it ejects a photon of light in order to go to the ground state. So so we can see that right here. Let's see how that happens. And still reaction, sucking wind. Okay. Go ahead, kill the lights. Hopefully we can have some remote success here. Lights. Oh. Ooh.
Okay, that's actually I guess that's how glow sticks work. Freaking whoa.
Dude, that's so sick.
You know, what can I say? Not everything can be an explosion. Alright, so this is the basic idea of what is behind those glow sticks, right? So you have two chemicals that are really bad for you, and when you mix them together, right, there's this chemical reaction that occurs and you get an emission of light. Unfortunately, I've seen this be a lot brighter before, so we're really sucking wind on demos today. So, there you have it. That is chemiluminescence. That worked not so well. And then, it was green before, right? Or blue, but now we're into a purple phase. Watch it. Watch it. Wait for it. Now it's darker purple. Wait for it. Wait for it.
Darker.
Now, if you sit up there with your, I was going to say your watch, iPhone, right? And you time that, you will find that the period between the color changes should be regular, right? And it will continue like that and oscillate throughout the remainder of the period. And again, you're seeing this evidence of this cycling of reaction. Here we're into a blue phase, right?
Green.
And then it's going to be a sharp change coming, going into a purple phase. There it goes. So there's the VZ reaction. Okay, right on. So that works. Next one we're going to try here is we've got a few going on over here. We've got the ethanol cannon, which is combustion. We've got electrolysis, which is combustion. Since we're talking about, we finished off with luminol, and we're thinking about the United States, let's think about this process right here. What we've got going on here is, first